How I would like to start the video today is that I just want to talk a little bit more specifically or in more detail about periodic functions. So far in ECET, you've encountered a variety of what we would call time periodic functions. And by time periodic, I mean that the quantities that you've been working with when you analyze circuits vary only as a function of time, if they're AC. For example, I've drawn a very simple little circuit here, and if we were to specify the quantities, we would say that V is more specifically, voltage is a function of time, lowercase v, open parentheses, t, close parentheses. Voltage as a function of time is equal to some value, some peak value of voltage, times the cosine of omega t plus or minus phi sub v. And this is the complete description of a sinusoidally varying voltage. And if we have a current flowing in that same circuit, we would write the value of I of t is equal to Vp times the cosine of omega t, sorry, not Vp, and a lot of trouble there, Ip times the cosine of omega t plus or minus phi sub I. And some points to make about this are that V is a function of t, and both V and I are written in lowercase, indicating that they are time variant AC quantities. We know that the voltage and current in this AC circuit are going to be described by cosine waves, and this means that they are periodic. And more specifically, they're time periodic, meaning that the value of the voltage is only dependent on this variable time. So in this equation, the voltage is the dependent variable, and the independent variable here is t, time. And that is also the purpose of writing V of t and I of t all the way out, to kind of indicate that those are time-dependent quantities. And the quantity inside the parenthesis indicates what variable the voltage or the current value varies upon. If we were to plot a general sinusoidal voltage or current that varies as a function of time, we'd get this plot right here. If we were to just plot the sine function as a function of time, this is a real generic one. This value here would be the peak value if we're talking about a voltage or a current. In this case, we just happen to be showing that it's 2 units tall. Since this wave here is a function of time, the dependent variable time is on what we would call the x-axis, and the independent variable voltage is on the y-axis. Any two peaks in the wave are going to be separated by a fixed amount of time, which is going to be measured in seconds. So the distance from here to here is a time measurement, and it's measured in units of seconds. And we call that capital T, it's called the period. And that's the time that it takes for two peaks to appear. And more specifically, the period is the amount of time it takes for a periodic function to repeat itself. So we can measure it from peak to peak. We can measure it from zero crossing to zero crossing. Really just any 2 points that are of the same amplitude. Since this is a periodic wave that is sinusoidal in nature, one full period, I'll remind you that the rotation from here to here is 2 pi radians, and that gives us the relationship between period and what we call angular frequency. If we take 2 pi radians and we divide it by the amount of time it takes to transverse those 2 pi radians, which was the period, we call that angular frequency, which is what is the argument of the cosine function here. So we've got 2 pi, which is just an angular measurement, radians. Period is again measured in seconds. Angular frequency, therefore, is measured in radians per second. So, and that, if you're not familiar with the Greek alphabet, that's omega. Lowercase omega, it kind of looks like a cursive W. Often, instead of angular frequency, we are concerned with knowing how many cycles a signal will complete in a given period of time. And the number of cycles that will be completed in one period is just the inverse of that period, and we call that frequency. Frequency is just the inverse of the period, which again was measured in seconds. This is now measured in hertz, and that's just called frequency. Since one cycle is 2 pi radians, we can write F is equal to omega over 2 pi, which gives us the fundamental relationship: angular frequency is equal to 2 pi times the frequency of the system. And remember, all of these have to do with units of time as the dependent variable. Other physical quantities may vary as a function of position instead of time. For example, I'm going to just draw a wheel, a bicycle wheel, in several different positions. And before the wheel starts rolling, let's pick one point. Let's say it's at the top. And as the wheel rolls, this point, this constant point on the circle of the wheel, is just going to move around. And so if I were to plot this, I would see that it looks kind of sinusoidal there. And the height of the red dot, that's what this is. This is a plot of height as a function of distance here. Right? I'm looking at the distance the wheel has rolled along this axis, and I'm plotting the height of the red dot. Here it's at its peak value, here it's at its median value, here it's at its minus peak value, and that's just going to repeat as the wheel rolls around. And what I'm showing here is that the height variable is dependent on distance in this case, or it's a distance harmonic function. So I would write this as h of x, and I would write this as distance, typically as an x in meters here. And what I've done up here is I've just plotted a sine function where the dependent variable is distance measured in meters. And much like the period is the space between peaks of a time harmonic function, wavelength is the distance between two peaks in a distance dependent function. And the cosine function that we would write for that is h of x, the height of that point on the bicycle wheel, is whatever the peak height is, times the cosine of beta times x. Well, what is beta? I thought we were talking about lambda here. Well, remember, in the cosine function, we put angular frequency, not period. So beta is the spatial analog to angular frequency. So again, if the distance that it takes for two peaks to occur is going to be lambda, and we go through 2 pi rotations, angular rotations in one complete cycle, that gives us the relationship beta is equal to 2 pi divided by lambda. So beta is measured in radians per meter. And so this is called, beta here is called the phase constant. That's its name, sometimes called the wave number. And it basically is the spatial analog to angular frequency. So we've got wavelength, which is analogous to period, and we've got phase constant, which is analogous to angular frequency. So you can see the similarities between the wave number and the period in a distance periodic function, and the angular frequency and the wavelength in a time periodic function. It would also make sense that in the spatial dependent system that there is an analog to frequency f, and there is. It's just we don't often use it, and it's called spatial frequency. You could calculate it as 1 over lambda. It's just not used very much, but if you're curious, it does exist.